totally work. All right, so hello everyone. Welcome. Only logistics update for you all is quiz 2 is due today. Yeah, good thing I mentioned it, I guess. Pro tip, one of the most useful things for both our course and basically for all your courses, I believe it's the home page here, there's like a syllabus thing. It's got a nice big old calendar of kind of when everything is due. I say a calendar. When you'll open our course, the first page, one of the most useful things is this giant wall of, hey, here's assignments and the due dates of it and things like that. So references from time to time, reference, you got your little to-do thing on the side. But yeah, make sure you all do the second quiz. It's due today. Hopefully you've already done it once already. And then this segues nicely. Remember, the purpose of these quizzes is not practice. The purpose of these quizzes is not practice. The purpose of these quizzes is to see if you've practiced enough. That's really what the purpose of the quizzes are. Do you understand this stuff? The ideal scenario is you go into this quiz and you get them all right kind of the first time, or roughly all correct the first time, because you've already done all the practice beforehand. That's the ideal scenario. I know time-wise it doesn't always work out that way. All that, various classes, things like that. But yeah, the main purpose of these quizzes is to give you problems that you have not seen before and see if you can solve them. In the same way, that's what the test is going to look like. It's a bunch of problems you have not seen before. Can you solve them? Now, ideally, when you've been doing these quizzes, you realized, oh, this looks like, if you've done the problem sets as well, you'll be like, this looks like this problem from the problem set. This kind of looks like this one. It's not identical, but there's similarities, really strong similarities. The same is true of the test, and I just sent you all an announcement yesterday about this, but I posted last year's exam as a practice test. The same logic holds. Do not use this test. I know it's called a practice test. Do not use this as your practice. Use this as a check. Use this to make sure. So basically, you do all your studying, and then you do this practice test to see if you're going to do okay on the real test. The thing with this practice test is once you've done these problems once, you've seen them before. Once you've seen them before, you're going to have a sense of how to solve them, which is fine. But if you want to use this as like a mock test, maybe that's another phrase of putting it, you can only really do a mock test once. After you've done it once, you've seen the problems, and it's not the same the next time you see it. When you all get here, we have our test on February 18th and February 20th. You will see those problems one time, and you will solve them, and that will be it. So this is a way to kind of like approach that in the same way. You can obviously, do with what you want with this, but that is my recommendation. Use this as a mock test after you've done all your studying to see if you understand it. And then the ones you don't understand, then that shows you what you need to practice more. But same thing, when you all take this, the dream is that you're getting most of these right. I also put in there that there's more questions. There's 25 questions here. That's more than I'm going to give you on the test. But basically, I was on the mind of I could either have given you less or more, and I gave you more so that you had more versions to look at, different types. 3 minutes per question is as much as you want to be spending on these timing-wise. 15 per question down here. And yeah, you can look through this. Oh, I need to fix this. This should only say 3Q, but whatever. Yeah. There you go. It exists. Use it as you will. The reviews even, so we're going to do a review, but the PowerPoint slides for those are there. The quicker questions are all there. So there's a bunch of extra resources already in this folder that you can kind of peruse through. But the most important thing is that you have been going through the problem set. That is, there is no substitute for practice. There is zero substitute that I have found for practice. It is how you learn in a STEM course, how the vast majority of people learn. There is a few exceptions of people who can just listen to me talk and somehow understand everything I'm saying. Those are the anomalies. And this is going to sound rough. Do not assume you are the anomaly. It's very unlikely. I'm talking like 5% of people are probably going to be in that category, just listening and understanding. Assuming that you are in that 5% is a dangerous assumption. You can test that assumption really easy. If you're like, I think I'm in that 5%, then you should be getting 100% on the quizzes every single time, first try, without having to do any practice beforehand, and without using any other resources, just doing it in the formula sheet. So if you are able to do the quizzes, first try, get every single question right by only using the formula sheet and no notes, and no other resource, then yes, you're probably in that 5%. Otherwise, practice. Yeah, all of you probably know that one person that's like, wow, they just get things. They are the anomaly. They are not the average. Do not. And so when you then look at that and be like, I should be like that, that is an unreasonable assumption. It's not a healthy one for you. All right. Electric potential. We're starting with PowerPoint slides, so we're getting on track. We're getting where I want to be. We basically need to get through this PowerPoint slide and then capacitors. And then that's everything for test one. So just a quick recap of what we've covered. Coulomb's law, that's the forces. So we talked about charges, we talked about K, Q1, Q2 over R squared, that's Coulomb's law. We talked about electric field, we talked about the equation for electric field, E equals KQ over R squared. We talked about an infinite distribution of infinite charges, we did the integral for that, and then we just did Gauss's law. And Gauss's law is just another way to find electric field. Electric potential is now going to be another thing, but it's going to be all connected. You're all going to see everything builds. Everything is connected to what I taught you before. Coulomb's law came from charges. Opposites attract by charges repel. Electric fields are what cause those forces. Electric potential is going to be another way to understand why charges move. It's another way to understand it. And the beautiful thing about this entire PowerPoint slide is there's no vectors. It's all scalars. So it's easier to work with mathematically. All right, so we're going to derive what it is, we're going to talk about what it is, and we're going to identify how it's practically useful. It's really easy for me to convince you this is practically useful. I know the title of this is electric potential. Another name for electric potential is voltage. So you've heard of voltage, so clearly it's useful. Like none of you, every single one of you has heard what voltage is. You might not know what it is conceptually, but you've looked at a battery and seen a V on it. Clearly it's useful. So, all right, let's see. There's going to be, anytime we kind of introduce one of these, there's usually a good amount of clicker questions to kind of warm you up to it. From 2048, you drop a water balloon with mass of 1 kilogram from the top of the physical sciences building, open to one with it. What value is the closest to the speed at which it hits the ground? I'll give you like 2-3 minutes on this. This does not use anything from physics 2. This is physics 1. See if you all remember how to solve this. And there'll be a reason why. You'll see. There's many ways to solve this, but there's one way in particular we're going to look at. Feel free to chat with the people next to you. Ominously quiet here. All right, give you all a minute. Give you 3 minutes. just go to 240, because I think most people not noticing much change in responses. All right, we'll close this out in 5, 4, 3, 2, 1. Okay, so I realize with this question, I probably need to update it to really force you to use one way. There's 2 ways you can do this. Kinematics is one way. Yay, we're not actually going to be using the kinematics for this. The other way, and the way that I really wanted to convey, this answer is the same. So just dropping it straight down would also be the same if you slid it down a frictionless hill, regardless of what that hill shape was. If you have something start 10 meters high and then it gets to the ground, how fast is it going? So the thing I wanted to kind of remind you all of is energy. Conservation of energy is one way to solve this problem. If you all remember conservation of energy, it's potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. This is from Physics 1. It's the idea that's going to be really important throughout this PowerPoint for us understanding some things. So, potential energy initial, you know, is mgy initial. You might have seen it as like h. I've started using y just because I like it a little bit better. So, where my starting height plus, 1/2 mv initial squared equals mgy final plus 1/2 mv final squared. Now, something important here, and you all are doing this in your labs currently, this y initial and this y final are all relative. You're actually going to see a question of that. Do I have that here somewhere? Maybe not. Probably not. Where do you all want to set y equals 0 at in this problem? The floor. Why is that convenient? Where does my object end at? The floor. So why is that convenient? If we set the reference y equals 0 as the floor, then that final term goes away. However, this problem works the exact same if you set y equals 0 as the center of the earth. Why? We only care about the difference. I'm actually going to write it out here. So instead of crossing that out, we're going to find here that mg times y final minus y initial equals 1/2 m, and same thing, we can have v, if I move things around this way, I'll move it this way, so it's actually, I'm not doing anything bad, I'm not doing anything crazy, I'm just doing algebra. So we have the difference in height, it's opposites of each other. Initial minus final equals the difference of the velocity squared, final minus initial. If you're like, why are they flipped? Algebra. It's just algebra. All I did was rearrange that equation. All right, why is that significant? All we care about is the change in height. This is delta y. So this is mg delta y. How much did my height change? This is still 10 if I go from 10 to 0. It's also 10 if I go from 100 to 90. It's also 10 if I go from 1,010,000 to 1,000,000. We only care about the difference in height when solving this problem. Where you set y equals 0 to is up to you, and it doesn't change anything. When you all are doing your Physics 2 lab this week and you're measuring the voltage across the surface, you're going to be doing the same thing. You're going to set when y equals 0, and how are you going to, in this case, v equals 0. Where are you going to set v equals 0? Wherever you put your black probe. Your black probe, you're saying, is v equals 0, and it doesn't matter where you put it, you get the same results either way. We're going to see that you're going to hear me mention this a bunch in this class. So, this problem, the m's cancel. So 1/2 m, v final squared minus v initial squared. Velocity here, we are going to set the reference frame where the initial velocity is 0. M's cancel. So we get g times delta y equals 1/2 v final squared. So v final equals the square root of 2 times g times delta y. It's just algebra. And you do all that, and I believe you get 14. I'm going to plug it in my calculator so I don't look silly. Yeah, you get 2 times 9.8 times 10, square root of all that. And yeah, you get 14 perfectly. How nice, right? All right. So, conservation of energy. It's useful. It's incredibly useful because we didn't have to do anything with vectors and things like that. And if you're like, but I did kinematics instead, that's fine for this problem. But what if instead your problem was a hill that looked like this and you had a box sliding down that hill? Good luck doing kinematics with that awful hill. But it's the exact same solution as this. That's the crazy thing with energy, is you can do problems that otherwise would be disgusting. You don't care what the hill shape looks like, you just care about the top and the bottom, and that lets you get the final velocity. All right. Now, we're going to do some derivations. Another check from Physics 1. This one I'm not going to give you nearly as much time. What quantity is determined by taking the dot product of force and displacement? Is it strain, constant, displacement, acceleration, or work? This is good for your health.
I mean, none of the other ones make sense. So my heart is feel. I am nothing without my force.
Alright, you all got 10 more seconds. This is either you know it or you don't. That's really all it comes down to. It's a definition. All right, 5, 4, 3, 2, 1. Okay, it's a definition. If you apply a force over some distance, what's going to happen is your thing's going to speed up. And the amount that it speeds up, we can calculate the energy of all that, yada, yada, yada. This is work. Work equals the dot product of F, and I'm going to write this a little fancier. Let's make it a dx. Why am I making a dx? What if your force changes over time, over your distance? And what if your angle between these also changes? So this dx is over a tiny, tiny, tiny little piece of it. So that says for tiny little pieces is true. As time goes on, that could change. So how do we get all the contributions of all the tiny pieces added together? There it is. Yeah, you all might have seen it this way. Work equals F dot, X, or distance, F dot D. They're the same thing, but the bottom one is better because it's more general. The top one only emerges if your force is a constant and if your angle between the force and the direction you're moving is a constant. This top one is derived from the bottom one. If F is a constant, you pull it out. If the angle is a constant, it goes away. So, it's work. And yeah, the logic with this one down here is, what if this is my path and my force is this way? You have to do an integral. Because the angle is constantly changing and you have to integrate over all of it. It's a grand time. Did you ever have to actually do that? Probably not. But the integral is better, and we're going to need that integral. Okay, I will also remind you from Physics 1, there's the work energy theorem. Work equals the change in kinetic energy. This is not a hard thing to convince you of. If you push something over some distance, you're going to get faster. That's going to make your kinetic energy go up if you're pushing the same direction, or down, opposite direction. And it's literally derived from doing this integral. The kinetic energy, the equation for kinetic energy is derived from doing this integral. So, again, Physics 1 stuff. But also, work equals the negative change in potential energy. Another thing you derived in Physics 1 that I'm not going to spend the time on. That's another relationship. So work equals a positive change in kinetic energy. Work also equals the negative change in potential. And if you're like, this is weird, how is this a true statement? If I just put these two pieces together, if W equals the top and W equals the bottom, then they equal each other. And this is literally this is conservation of energy. This is how we derive conservation of energy. Conservation of energy is kinetic energy final minus kinetic energy initial equals potential energy initial minus potential energy final. It's negative, so it flips the direction. Oh, rearrange that equation and you derived conservation of energy. So just to remind you all this energy stuff. So great, there's the integral, great, there's the some definitions that we need to remember, some relationships. We're going to use those for derivations. Even if you don't remember them, you definitely need to know conservation of energy. You definitely need to know energy initial equals energy final. Yeah, if you all know that, you're good. Okay, so let's go through some logical steps here. The force done by a charge, remember by an electric field, is Q times E. If you're like, where did that come from? Remember E equals F over Q. And then algebra. So you know, there, great. Why is that useful? Oh, we can put it in our work equation. If you're like, where did this come from? This change in energy equals that. Just to kind of fill in some steps. Work equals negative change of potential. Work also equals the integral of F dot dr. Instead of dx, we put dr because it's more general. Oh, then they equal each other. If A equals B and B equals C, then A equals C. So we just set those two things equal to each other. Pull out the Q, it's a constant. And now we're going to do an integral for E. So this is the setup. We're deriving the energy. If you're like, what are we doing? Remember, we got to keep our eyes on the objective. What are we actually doing here? We're solving for the potential energy stored in electric fields between two charges. The energy stored in that system. Because energy is useful, so it's very useful for us to determine the energy stored between charges. Why is that important? If we know the energy stored between charges, we can predict what's going to happen when we release them. When you release them, it's the water balloon problem. If I know my initial potential energy, and I know my initial kinetic energy, we can use that to figure out the final kinetic energy and things like that if you release it. That's the motivation here. Energy is great. How do we know energy is great? Because the water balloon problem and the hills problems and all the problems you all did in Physics 1. It's just as useful with charges, but we need to find some new equations. Yeah, who knows? They escaped. All right. Okay. So do I want to do it this way? Yeah, so this one is fine. It's going to be really, the wording here is kind of, you might get lost in it. I'm just going to derive that expression that we wrote before. So like, I'm going to read this, and then I'm going to write it in math, and maybe that'll make it easier to understand. 2-point charges, Q1 and Q2, are initially on the x-axis. One's at 0, one's at x equals xi, respectively. So one charge is here. That's charge 1. The other one's over here. That's charge 2. Drawing some pretty pictures. How much work must be done to move charge 2 to a new direction, a new position, xf? We'll just make xf to the right of it. You know, we're going to do, and try to move it over here. Try to move that charge from one location to another. How much work is required? How much will my energy change? Work, energy, they're interconnected. How much will I gain energy in the system? Will I lose energy in the system? Let's figure that out. How do we figure that out? We have a nice little equation. The change in energy is negative Q times the integral of E dot dr. Where did that come from? The last slide. There it is. It's a thing at the bottom. Okay. Now we're just going to actually do this integral. Q here is the Q that's the charge that's moving. This is the charge experiencing the force. So that's Q2. E is the one making the field. One makes the field, one experiences the field. In this case, charge 2 is the one experiencing the field. Charge 1 is the one making the field. What is the electric field due to a point charge? Let's see who knows that. It's an equation. It's on your formula sheet. Who knows it? Shout it out. There's a K. I'll give you a hint. It starts with a K. There we go. You know, see, there you go. It's the electric field due to a point charge. Nothing crazy. There it is. Now, I will tell you we're going to change this dot product into, remember we can write a dot product as the magnitude of E times the magnitude of dr times the angle between them. Great. I'll tell you in these problems, this angle is always going to be 0. The reason is this r vector points from 1 to 2, and then the electric field we just always kind of define as pointing radially outwards, the way we do this. So that's always going to be that. So angle's gone. dr. And what are my bounds of my integral? Where am I moving from and to? Where does Q2 start? Xi. Where does it end? All right, great. You all do this integral. It's easy. This is a Calc 1 integral. You're deriving the equation for electric potential energy by doing this. So you get a negative Q2 times a K times a Q1. Those are all constants. They get pulled out. What's the integral of 1 over r squared? 1 over r. And then there's one more thing I need as well. What else do I need? Be confident. A negative sign. Because it's on the bottom. If you all took the derivative of this, this is r to the negative 1. So it spit out a negative 1, the power would go down to negative 2. Yeah, and the negative signs get killed. And we evaluate this from xi to xf. So you just get, k, q1, q2, q1, q2. We start at xf minus k, q1, q2. We end at xi. Ta-da! Okay, these are basically the expression. This is basically the expression for the energy stored to charge. The only thing we're going to add to this, instead of starting my thing at x op, so what I would like to do here, 2 terms is gross. 2 terms is more than I want. I want to get rid of the second term. So my next question for you all is, what can I make xi such that the second term goes to 0? And in fact, you know what? Let's make that. Yeah, let's just make that a clicker question real quick. Yeah. I can do whatever I want. I'm allowed. The change in potential energy due to moving a charge near another charge is given by U equals KQ1 Q2 over xf minus, then I just copy and paste this and change it to f. xi. What can I set xi to in order to make the second term go to 0? And I have to put answers here, and it might give away too much. All right, can I set xi to 0? Can I set xi to anything I want? Can I set it to infinity? Can I set it to xf? There you go. There's a bunch of hodgepodge answers. Which one will make the second term disappear? So this is a clarify. There's no physics here. Yeah. Yeah, AA. Yeah, that's a classic frequency. You can set different frequencies if there's other classrooms around, but there isn't. So we're good. All right, give you all about 15 more seconds. Again, this is a, how's your math? All right, in 3, 2, 1. Okay, so let's just go in order. If I set xi to 0, what happens when you divide by 0? It's bad. It's undefined. If you said like the limit as x goes to 0, it's still bad. It blows up. It goes the wrong direction. Anything I want, definitely not. You know, if I divide by 5, it doesn't equal 0. Not a hard thing to convince you of. Infinity, and this is where technically, you know, we're supposed to say the limit as it goes to infinity. But yeah, if you divide by a really, really big number, you know, make it whatever you want. What is infinity? A really big number. How big do you want it? You know, 10 to the 25. If you plug in your calculator 1 divided by 10 to the 25, you're going to get a number that's basically 0. Infinity, if you divide by infinity, it's effectively 0. And what is infinite but a really big number? I think that was one of the most useful things I heard a teacher ever say when I was in your shoes. It's just such a big number, it might as well, it ends up being 0. It's such a small number. So, what is the purpose of this? What is the purpose of this? This means if I have one charge, charge 1, I'm going to zoom out. If I put Q2 way over here, infinitely far away, you can't really see it. I know red and black's not good, but it's way off to the right. How much energy does this system have? None. It starts with no energy. And then as you bring it in, what am I doing? I'm building the energy of the system. How do I know I'm building the energy? How do you all know? You know, I raise this water bottle. As I lift its height, am I increasing the potential energy or decreasing it? Increasing it. How do you know that? Outside of the equation. What tells me that I'm storing energy here? It's more height, but experimentally, how can I test that I have more energy stored here? If I drop it to a bigger height, it's going to be a faster thing at the bottom. When I bring this charge closer and closer and closer, how do I know I'm storing energy? The closer I get it, if I released it, it's going to go faster, way far away. This is stored energy. Why is it stored? What's the word stored mean? It means you can release it. So when I bring this charge from infinitely far away, and I bring it all the way over here, I have stored energy. How much energy have I stored? The distance between them is r. That's the amount of energy I've stored. The second term disappeared, and I'm just left with the first term. So this is the energy stored between two charges. That's the derivation for it. And this energy that's stored is useful. Stored energy is incredibly useful. All about it. Most of society is just taking energy from one form and converting it to another. And if we can stockpile that energy, then we can have it when we need it and when we want it. Batteries, you know, all that good stuff. So yay, you did it. You derived it. The energy stored between two charges is K, Q1, Q2 over R. It's very similar to force, but it's missing a square. Do not mix that up. Yeah, great question. Let me draw a picture of this. Yeah, this is Q1, this is Q2. And then R1, 2 is the distance between charge 1 and charge 2. I could have done the same thing with Coulomb's law, where I'd put R1, 2, I just didn't. It's energy. It's the potential. What does the word potential mean? The ability to store, there's a possibility that this thing can do work. Right now, it's not doing any work. How do I make it do work? I let it go. I release it. And then I can hypothetically ask you a question. How fast would it be going? And it would be the water balloon problem, just with the new equation. Instead of using mgh, we now have a new equation for energy. Does So, there you go. That's the energy stored between charges. Yeah, that's such a good question. Does the mass of the particle matter? So how would we use this basically comes into play. How would we use this? Remember that the negative change in potential equals the change in kinetic. That's just a rearrangement of conservation of energy. Kinetic has mass in it. Kinetic, the kinetic term has mass in it. So if you had an object with more mass, it will end up going slower. Because, and if you think back to like forces perspective, it experiences less acceleration because bigger mass, same force, less acceleration. So yes, the mass does matter. It doesn't affect how much energy is stored. It just changes how much kinetic, how much velocity you're going to get at the end. Yeah, love that. All right. I'll leave this here because we're going to keep using it. Like, this is conservation of energy. It's just written another way. To remind you all that this is the exact same thing, I'm going to write it this way as well. Potential energy final equals this. Because a lot of you are cool with conservation of energy, but sometimes when we write it a different way, it throws people's brains for a loop. But there you go. I gave you one more step to see that they're the same thing. Okay. Great. Let's see if we're good with these. If I have two charges, both positive, what happens to the net potential energy? What happens to the stored energy in the system if I double the distance between them? Does the energy, do I get twice the energy, half the energy, the same energy, or 1/4 the original energy?
Yeah, it makes sense to go smaller. If you go like this. Yeah, there needs to be a square.
All right, give you all about 15 more seconds. All right, 5, 4, 3, 2, 1. Okay, so remember the technique for doing these. We haven't done one of these in a while, which is a bummer. I probably should have included more of them. Remember that our original energy, we put a little 0 for original, is K, Q1, Q2 over R. Really the question here is, did you accidentally square R or not? That's really the major thing that you might have done if you made a mistake. My new energy, let's call it 1. K is the same. Q1 is the same. Q2 is the same. My distance is double, so I put a 2 in front of it. Then I pull that 2 out to the front. And we see that my new energy is 1/2 the original energy. 1/2 UE initial. There's your answer. It's half. So if I told you one charge doubled, the other tripled, and the distance increased by 10, the same process works. You just put those numbers in front of it, pull them all out to the front, and life is good. But yeah, the question is, and really the main purpose of this question, 1, to remind you of this, 2, don't square it. This is where I'm warning you all that you have force, and the equation looks almost the exact same, but the distance is squared. Do not mix up force and energy. They look similar, but they're not the same. One, F is not a U. They're not the same variable, and then the equation reflects that they're not the same. They're solving for 2 different things, and they have a slightly different equation accordingly. Okay, this looks crazy. You're going to look at this and be like, what the heck is going on here? What I need to convey to you all is as we add charges, so the logic here is you have to build the system. So I'm actually going to kind of show you this next one, and then I'm actually going to tell you how to solve it, and then let you do it. So here's the system of charges. There's 3 of them. 1, 2, 3. And my question to you is, what is the stored energy in this system? How much energy is stored in this entire system? The technique for solving this is I'm going to build it one charge at a time. So what I need you all to do is I need you all to find the energy required to bring one charge in when nothing is around. How much energy is required? We'll call it U1. The energy required to bring one charge in when nothing is around. That's the first step, okay? Now, you're going to find the energy to bring a second charge in, a distance r away. Okay, how much energy is required to make that happen? And then lastly, how much energy is required to bring a third charge after the other two are here? So, you're bringing one charge, then you bring another, then you bring another. And the key here is you have to think about as you're building this, you know, what's it having to fight? How many charges is it going to have to fight and things like that? And if you all want the total energy of the system, you add up these three terms. The energy of the system is not the energy of U1, it's not the energy of U2, it's the energy, it's all of them together. One charge at a time. You bring one in, then another in, then another in, then another in, then another in. So my question to you, oh, sorry, this one, okay. It's a little bit of a bummer here. Actually, I'm going to just change this problem entirely then. So, because right now my wording doesn't match that, and I think the way I put it here is actually better. If I have two charges, we're going to change this. What is the energy stored in the following system? And I'll change electric potential energy. The previous problem I had is good, but I like this one better. And I'll, of course, change the answers because none of these make sense. Is the energy kq squared over r? Is it 2kq squared over r? Is it 3kq squared over r? And then let me double check. If I just put all of them, eventually it'll work. 4kq squared over r. I think that's enough of them. You know what? Or 0.
But the thing is, the two R's are equal because equal R right now. So is it actually 3? I'm just gonna send it.
All right, I'll give you all about 20 more seconds.
I trust it more than I trust you, but I feel.
All right, in 5, 4, 3, 2, 1. All right, so let's solve for each of these energies. Let's solve for U0. How much energy? So the way to think about this, if we kind of go back to our original equation, you're going to be like, this is just to help us understand it. We're not actually going to use this equation. Remember, y'all, that change in U equals Q integral of U dot dr. If you're like, what? Remember, this is how we derived it. We're not actually going to use this integral, but it helps us just remember some things. This energy happens because we're fighting. we're fighting other charges. Well, kind of. In this case, when I bring U1 in, am I fighting any other charges? No. So how much energy is here? 0. There's no force that I'm having to fight against to make this happen. It's free. If there was no other charges in the universe, you could kind of move this charge around and you would not store any energy. You know, if you move a rocket around in space and there's no planets around, you're not increasing or decreasing your gravitational potential energy. Because why would it? There's nothing pulling or pushing on it in space if you move it around. All right, so U1 is 0. We already derived this one. What's the energy required to bring a second charge in? K, Q1, Q2 over R, not squared. Don't square it. It's so tempting. I know we've said squared so many times. Just K, Q1, Q2 over R. How much does it take to bring the second charge in? You got to fight the first one. Now, in this one, when I bring it in, how many charges am I fighting? When I bring in this top charge here, how many charges is it having to fight? 2 of them. So what's the energy? U2 is going to be the energy required to fight one of them. Let's call it Q1, Q3 over R. And then we also need to fight the second charge. So that's going to be Q2, Q3 over R. It's how many charges are you fighting to bring it in? So what's my total energy? You know, my net energy is just U0 plus U1 plus U2. 0 plus KQ squared over R. They're all Q's, so you don't need to distinguish between them. Plus KQ squared over R plus KQ squared over R. So how much energy do I have in my system? 3KQ squared over R. Another way that you can actually do this problem is you basically want to multiply, okay, what's the energy between charge 1 and charge 2, charge 1 and charge 3, and charge 3 and charge 2. You want basically every pair possible, is effectively what we did. I can kind of write that out for you all here if I had done it a little bit better. Another way to kind of wrote this was 0 plus K Q1 Q2 over R not squared, plus K Q1 Q3 over R plus K Q1 Q2 Q3. It's every permutation possible. What's really important here is as you add more charges, it gets more and more difficult. The next term, if I brought a fourth one in, it would have to fight 3 charges. If I brought another one, it'd have to fight 4. If I brought another one, it'd have to fight 5. The really interesting connection, you just connect this to the real world. This is why your battery on your phone charges slowly when it gets to 90%. It's harder and harder to bring more charges in because you're fighting all the other ones already on there. It gets harder and harder to do that. But you store more and more energy kind of at that topper point as well. That's why your battery tends to last the longest at that 90 to 100%, and then as you get down, it goes quicker. It all connects. So, have a good one, y'all. We'll keep chatting about energy. Next time, we'll hopefully get to voltage. That's a dream on Friday. We have not talked about voltage yet. Haven't gotten to it.